So you will see the quiz sometime later today or tomorrow, probably tomorrow. But remember, it's not graded, so you don't have to do it. Today, what we're going to do is we'll start with a couple more examples from 3.9 of the type that's pretty much always on the final. And then we'll quickly look through chapter 1. And then tomorrow, we'll go over questions. So as usual, I'm kind of skipping homework. So we'll go over any homeworks you have questions on in 3.7, 3.8, 3.9, and then do a little bit more of chapter 1. Because again, chapter 1 is not on the final, but if you're taking Calc 3, it is assumed that you've seen it in Calc 3, so we go over it quickly, but we're considering it review, so it makes it easier for you if you've seen it already. So, example. Let me draw the picture first. So I don't mess things up like I just did. So we have a square pyramid for a tank. With a height of 100 meters. Base width of 200 meters. There's water up to 60 meters. And remember, the density of water is 1,000 kilograms per cubic meter. So find the work to empty it from the top. Sorry again about the writing. It's trying to smooth out again. So you can see I've drawn a generic line in the middle there, space here, and that's a W there, which is the width of that place. And you can see in some sense there are two distances we care about, those two. The top one is the height of the smaller triangle, which we're going to use to get W in terms of X. So we need to hide the small similar triangle. And then, actually, what am I doing? I knew I was doing something else. From top to a platform, because otherwise we don't have to. 50 meters. 50 meters up. So ignore this one. We don't need that one. So there are two distances we care about. So the original one I talked about, is the height of this small triangle. And that second line is the distance from the line to the platform. So those are the two distances we care about, which means we want one of those to be x, and then we'll fill in what the other one is. And it really doesn't matter which you use. What I'll do is, after we do one, I'll flip it. So let me just start with, suppose this is x. Then what is the other one? So what is this? Sorry about getting a little busy for a picture. So if the distance from that line to the top of the pyramid is x, so x is, let me make it more prominent, distance. So the distance from the line with w to the top of the pyramid. So what is the distance? Right, so x plus 50, because it's the distance x plus the distance. So the distance from w to the top of the pyramid. And I'll rewrite this in a second. Plus the distance from the top of the pyramid to the platform. My second original one would have been something like that. So we got to go through steps. And of course, once you get used to this, you don't have to go through all the steps, which is obviously a is equal to w squared, which means we're going to need to get w in terms of x. So what's the relationship between w and x? So this is where the similar triangles comes in. So w divided by x is equal to what? So our area, which remember is also a volume in essence, is 4x squared. And therefore our force is that. And then we have to multiply by the density. And in this case, because it's kilograms, we also have to multiply by 9.8. Therefore, and I'll leave off the limits for the integral in a second, our work is our force so the x plus 50, again, if you look at my picture, the x is the distance from the line to the top of the pyramid. And my second line, the x plus 50, is that distance plus the distance. So this is a 50 there. So the distance from my generic line with the w on it to the top of the pyramid plus the distance from the top of the pyramid to the platform. Right? So this is the force. And in this case, looking at my picture, what is the distance I move that generic line w? And in some ways, it comes back to the question, which is it is kind of by design x plus 50. And now we need the limits. And here's where we remember that what we're doing is we are moving the pipe down from the top, and lower limit will be where we first hit water. So we get, yes, so the 40 to 100. Which is, the 40 is, make that more obvious. 40 is the distance from the top of the pyramid until I first hit water, which is 40 meters down. And that's supposed to be another 0 there. And then I keep going until I get to the bottom of the pyramid. So there's one way of doing it. If I flip it, and so you can see what's happening here is, so if I put in X, then I am 40 meters down for the top of the pyramid. That one, I will move 90 meters, which is what we get for the X plus 50. And if I put in the 100, I'm at the bottom of the pyramid, 100 meters down. And at that point, I move 150 meters to the top of the platform, which is, again, the X plus 50. Actually, nothing I do here. I was going to switch them, but let me bring that to the other next line. So first, any questions on this? And I'll bring this picture over and I'll switch X. So any questions on this? Okay. So let me draw the same picture, but switch, and you'll tell me what we would get. We're not drawing all the numbers again. So again, we have the two numbers we care about. I'll give myself more space. These two. And in the last one, I let X be the distance from the top of the pyramid to the generic line. This time, let X be how far I move it. And so now the question is, what is the other distance I care about, which is this one? Right, so the X minus the 50. And so we get something similar to the last one. Again, we have the same type of thing, W, but now the height of the similar triangle is the X minus 50. So we get this. So this is now the force. And what is the distance in this case? Yeah, so just X. And what are the limits? Actually, since we're using, I should probably put in that this is a 60. So when I'm moving down from the platform, I first hit it at 90. And I keep going to the bottom, which is at 150. And if you look at it, this really is the same as the last one. Right? Because when I put in 90, I get 40, which is where the limit for the last integral came from. And I'm moving that 90 meters. Again, the same as what we had in the last integral. If I put in 150, I get 100, which is the upper limit of the other one. And if I put in that, I move 150. So if you put in the two endpoints, you'll see you're getting the same thing of the function we put into the integral. So if you look at it, so what we're looking for is I'm moving down from the top. And since X is the distance from the top, it's where do I first hit water? And so you can see it's at that first line inside the triangle, which is supposed to be way before the top of the water. So you can see since the water is 60 meters deep, there's 40 meters of empty space at the top. So I'm moving down. I move to the top of the water, which is the 50 meters down to the top of the pyramid, plus the 40 meters of empty space. And then I keep going until I get to the bottom of the pyramid, which is the 50 meters until I get to the pyramid and height of the pyramid. Is that okay? I should say, for this one, we pretty much never have you actually do the integral, even though you can see it's not actually too bad. We're just getting a cubic. But if this does become a multiple choice, you might have to simplify things. So obviously, the 4 times 1,000 times 9.8 is just a number. So you might have to multiply it out, which one it is if it's a multiple choice question. And since these really are the same thing, as I said, if you plug in the 2 endpoints, you'll see that we're getting the same thing for what's inside the integral. It doesn't matter which one you do. So any questions on this one? Okay. So let me do one more. So pretty much we just have the 2 main types. Pyramids where the cross-section is a square, and cones where the cross-section is a circle. Because we, of course, assume you know areas of rectangles and circles. So next one, let's do a cone. And just to be different, let's make it upside down. So a cone has a height of 60 feet and a base diameter of 30 feet. If it is filled to a height of 50 feet with water, this time I won't have a platform or underground or anything, just basic tank. So height of 50 feet with water, find the work to drain it from the top, to empty it from the top. And now the ones I did in the other one make sense. So again, you can see that there are 2 distances that we're going to care about. So let me put in my generic line. There is the height of the little triangle, similar triangle, and the distance we move that line to the top. And again, it doesn't really matter which one you let be x. Since those are 2, they're going to be both used. So again, let me just choose one of them to be x. Say that. and then you'll fill in what is the other. Oh, this is a cone, so I should do this. So 60 minus x. This is a circle, so of course the area is pi r squared. So you can see the first little thing is just trying to check to make sure you're paying attention, which is you're given the diameter here. So really what you want to do is break everything into radiuses. So I really want is the radius. So what's the relationship between x and r? So r over x is equal to the 15 over 60. So that's supposed to be 1/16. Why is oh, so the in some ways I don't really want to, might be able to. So you can see there are the two similar triangles. One is the full triangle, which has a height of 60 and a radius of 15. And this is our similar triangle. And we know that the ratio is for the equivalent sides is the same. So x isn't equal to 60, but r over x is equal to 15 over 60 because they're similar triangles. And again, for the force, we multiply the volume or area times 62.4, the density. In this case, because it's in pounds, which is already a weight or a force, we don't have to multiply by gravity. And what do I multiply that by? It's supposed to be a 60. And here it's kind of backwards, but what would be the limits for the x? I'll explain why. So that would be if I switch the x. So yeah. So this in some ways is backwards. So you can see x goes from 0 to 50 because x is the distance from the bottom to where we are. And therefore there's water from 0 to 50. Therefore x is from 0 to 50. The reason that's sort of backwards is really we're moving the pipe down, and the pipe first hits water at the height of 50, and it goes down to 0. But as I said on Monday, we don't care about the sign, or I'm not going to care about the sign. So in some sense, a positive, negative work just depends on who you're looking at. So if I'm pumping the water, I might get a positive value, but then the water is sort of doing negative work on me. So I don't worry about the sign. But if you want to go 50 to 0, that would be fine also. In this case, unlike the last one, it's really easy to flip them. So if I did the same thing and instead, so here are my two distances that I care about from above. Then pretty much I just flip everything. So wherever I see an x, I'm going to put a 60 minus x, and 60 minus x becomes x. And the only question is, what are the new limits? And 10 to 60. And this is about the only reason you might want to do the above integral, the first integral from 50 to 0, because again, you can check that we're really doing the same thing, which is if I put in 10, this is 50 times 10. If I put in 50, this is 50 times 10. So I'm getting the same thing. If I put in the 60, I get so if I put in 60, I get, because that's the bottom, I get 0 times 60. And if I put in 50, if I put in 0, I get 0 times 60. So you can see it, again, if you put in the endpoints, I'm getting the same thing inside the integral. So again, it doesn't really matter which way I do it. It's just that in this case, one of these integrals is going to be the negative of the other one. So any questions on this setup? So that is the last thing that we do that's going to be on the final. So as I said, for tomorrow, what you should be doing is look in 373839, look at the homework, and we'll go over at least a couple of the ones from the homework. Otherwise, what we're going to do today is, and you'll see it really is very quick, we're going to go through some of the stuff in chapter 1, which is assumed you have seen in Calc 3 if you go on. But so less chance for this part. Move on. Any questions on this one? Okay. So chapter 1 from the Calc 3 text. So 1.1 is in some ways kind of a real analysis type section, and you don't really need to know it. So they will talk about the definition of open and closed and compact, and they'll do it in some detail. You just need to have a vague idea of what it is. So 1.1 for us and for Calc 3 is just a really quick section where you should have vague ideas, except for one little thing, which is something you've probably already seen. Which is the distance between 2 points. And this sort of goes with vectors, which is the next section. How do I get the distance between 2 points? It's really just Pythagorean theorem. If I have 2 points, I do square root So you can see in 2 dimensions, if I have the 2 points and I want to get the distance, then I can get that distance using the Pythagorean theorem, because this is just the change in x, this is the change in y, and then this distance is the square root of the change in x squared plus the change in y squared. And this is what makes Euclidean space, hence the title. So in Euclidean space, we're assuming that this is the distance between 2 points. In non-Euclidean space, there will be different distance. And the reason you might have that, for example, is if I'm moving through the air, then the density of the air is changing as I move up. And so the difficulty of moving will be different as I move up, which is why it might make sense to move up quickly, because there the density is small, and then go across, as opposed to doing the usual just straight line. So in some sense, 1.1 is saying we're just doing what we usually do, which is just the regular distance between points, but preparing you for that fact that in later courses, on not Calc 3, but I mean upper level math courses or upper level physics or something like that, you might be getting into places where the distance between 2 points is something different. So it's saying, for this course at least, and for Calc 3, we're staying with the basic definition. And then the other ones they do in this section is, what does it mean to be an open space? And they give kind of that definition, which you need if you're doing something like real analysis. For most of calculus, you just need kind of a vague sense. So in 1 dimension, think an open interval. So endpoints are not included. Or if we have something in 3 dimensions, so suppose I have a solid sphere, you'd be open if the skin of the sphere is not included. That is open, but there are other ways things can be open, but we don't need them. Same type of thing, you just need the vague idea of what it means to be closed. Which in the simple case is just saying that the boundary is now included. So in 1 dimension, it's just the interval where the endpoints are included. If you're in 3 dimensions, again, if I look at my solid sphere, now to make it closed, I would include the skin of the sphere. Finally, compact, which is closed and bounded. The bounded, that's supposed to say bounded. The bounded part is just that nothing goes off to infinity in the space we're looking at. And the idea is, the reason we care about this last one, this will come up in Calc 3 when we're looking at finding minimums and maximums, is if we're looking at a function and it is compact in the region we're looking at, then there will be a maximum in that region and there will be a minimum in that region. So similar to how you would have found minimums and maximums in Calc 1, which is you can always get relative mins and relative max, but if we're looking for the absolute, then if it's closed, so if you're looking at a closed interval, then the maximum will occur either at a critical value or one of the endpoints. Whereas if it's an open interval, you might not get the maximum. And that's really all you need. So this is all you really need from 1.2. The idea of the distance between 2 points, this vague idea of what open means, this vague idea of what closed mean, and the fact that compact means that it's closed and nothing goes to infinity. And for this section, even if you're going into Calc 3, you don't have to worry about the homework. So as long as you have these vague ideas, you're okay for Calc 3. So 1.1 for us is really quick. So any questions on this? So 1.2. Which is now, instead of thinking of things as points, we're thinking of them as vectors. And if you've had physics, you know that a vector is something that, which I'll write in a second, something which is designated by a length and a direction. In particular, when we write this is shorthand for really the vector from the origin to that point. And as I said, a vector consists of both a length or magnitude and a direction. First little thing, let me see how many people have seen this, and this goes with the last section. Although I should have made nicer numbers. What is the magnitude of a vector? How do you get that? We sort of have done this in section 3.3, but just reminding you. So what's the length or magnitude of this vector? Oh, it is an easy one. What are we doing? It's just, again, Pythagorean theorem. So magnitude or length is just square root of the sum of the squares. Before I do direction, so that's length or magnitude. A unit vector U has a length of 1. And definition. Kind of a round circular definition, but it works. The direction of V is a unit vector in the same direction. Okay. So the direction of the 2, 1, 2, so let me bring this on the next page, but let me break up the vector 2, 1, 2 into its two pieces that we care about. So if you're doing two dimensions, you might be used to doing angles to give the direction. But once I move past 2 dimensions, angles don't really work very nicely. So for example, for 3 dimensions, I would need 2 angles. And if I had 4 dimensions, I need 3 angles, whereas here I can do it with 1 number. And that sort of gives what we can define as parallel, which is V and W are parallel if their unit vectors are basically the same. And they're the same direction if one is a constant multiple of the other, and that constant multiple is more than 0. So here it really is. If you get the unit vector, they have the same unit vector. So 1.2 is basic vector stuff. It also does addition and scalar multiplication, which we sort of use, but not a lot. So let me actually ask, there aren't that many of you, have any of you not done anything with vectors yet? That was kind of a double negative type thing, but so have any of you not seen vectors at all? So that's 1.2, just what's the length of a vector, what's the direction of a vector, how do you add vectors, how do you multiply by a scalar? In some sense, not too much. So for example, here are 2 vectors. We call it U and V. Oops, backwards. U. So that's telling you that V is 3 times as long as U. So I guess you can say it means that. But if it's a negative, it would mean, so if it was V was negative 3U, then V would be 3 times as long and in the opposite direction. So it gives kind of the difference between their 2 magnitudes. But the main thing is the fact that there is such a C is saying that they're pointing in the same direction if C is more than 0. So any questions on this? So let me quickly do the beginning of, so unlike these two, so these two, 1.2, 1.1, there's almost nothing you need to know, just the vague ideas. 1.2 is really basic vector stuff, which we'll be using in the next part. And the next part we will not. I will not assume you've seen it, even though you probably have. So today we'll just get to the definition and how we do it, and then tomorrow we'll start that, and we might quickly look at cross product, which is the other way you put vectors together. And that's pretty much as far as you need for Calc 3. That's what they've assumed you've seen. So let me talk about where this comes from. So we just did work is equal to force times distance. But suppose I have something like this, which is I'm pushing something along the ground, but I'm not pushing along it, I'm pushing at an angle. And let me put in an angle. And let me make a right triangle and stuff. So in this case, what would be the work I do using that force to move that object that distance? So it's still sort of force times distance, but what is it really? Right. So the idea is, typical physics thing, what I need is I need which will become the projection, which we'll do tomorrow, is we just need the part of the force that's moving in the direction we're moving. And you can see that is, and I'll do it this way, so this is the force that we care about. The length of F times cosine of theta. And then I multiply by how far I moved it. Right? So since that comes up a fair amount, we're going to do a definition. The dot product of u and v is basically that. The length of u times the length of v times cosine of theta. So this is the definition of the dot product, which you can see is basically made because it is the work if I'm using a force to move a distance and they're not necessarily in the same direction. So here's the background. So the dot product comes from the physics. Turns out, and this is where I'll stop, that there's an easier way of doing the dot product if you actually have the vectors. So in this one, it looks like what we need is both the vectors and the angle between the two vectors, but it'll turn out that we don't really. So I'll rewrite that in a second. Here I'll make them three-dimensional, but this will be true whether they're two-dimensional or three-dimensional or 4 or 20. And this obviously will be something we'd have to show, but I'm not going to because it uses a law of cosines and stuff, which I'd have to remind you of. I'd have to remind myself of, actually. And we keep going. So for people who have done this, do you remember how this works? So how do I take the dot product of two vectors? And let me actually, this might be easier to say it. So either for the general one or the specific one, what is the dot product? So it's just first entry times first entry. So this is equal to first entry times the first entry. It's the second entry times the second entry. And then however many there are. So in this case, it is the 2 times -1 plus the 3 times the 4 plus the 5 times the 3. So that's 25. So the dot product gives us back one number, and that makes sense from where it came from, which in this case, this might be the force, and this might be the, how far we move. And so this would then be the work doing that. So let me stop there since this is not the final, but what we'll do tomorrow is after we go over homework, I'll use this, we'll get the projection, and then I'll at least quickly say what cross product is and what that gives. So any quick questions on, or any questions on this? It depends on what you mean. So if, in some sense, no, not in some sense, it's no, because either what we need is the vector itself, like I do in this last example, or I would need to know the length and direction. So if you mean, can I do it with just what I have in this last example, I can, but that implicitly is giving me the length. So in some form, we need the length, yes. Unless you mean, so if I made it something like this, I could still sort of do it. It's just that my answer would involve a variable. So, yeah, so in some form, if we want to get a number answer, we'd need the length of each of the pieces. Except the only little case where it's not is in something like this. What is the work for this particular case? Zero. So if we knew that the force was perpendicular to the distance we're moving it, we wouldn't need to know the actual length. So there's that kind of simple case where you don't need it, but pretty much anywhere else you would need it. And this actually goes into what we're going to do tomorrow is if we have two vectors that are perpendicular, their dot product will be 0. Any other questions? It's only do the usual thing. I'll stop recording, and if you have more specific questions around.